The history of math is our intellectual foundation to understanding science. Science. Beautiful, awesome, wonderful science. It's the creative foundation to our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. This podcast is sustained through your generous contributions, which I am so very grateful for. You can visit me at mathsciencehistory.com. Click on that coffee cup on the right side of my website and buy me a cup of coffee. Or 2, or 3, or 4, because every cup of coffee that you buy keeps this podcast up and running. As we enter into the second season of Math, Science, History, I want to thank my listeners for following along. This has been such a wonderful year. It really has. And now that summer is officially over, I will be putting the podcast out every 2 weeks. This month, I have been inspired. As a podcaster, I really have come to love podcasts. These last 6 weeks, I have been listening to a fantastic podcast called The Industrial Revolutions, hosted by Dave Broker. Every month, Dave puts out a long-form podcast that provides an extraordinary amount of fantastic detail about how we, as a primate species, have evolved to create a world filled with inventions, technologies, and various forms of mass transportation, all while enduring societal and economic changes. Industrial Revolutions is a podcast that reminds us that we are a resilient species. Without a doubt, these are thought-provoking and informative podcasts. And you can find the Industrial Revolutions on your podcast app and at industrialrevolutionspod.com. I'm also going to provide a link to his podcast on my website as well at mathsciencehistory.com. This month, Dave's podcast, called Springtime of the Peoples, addresses the end of the first industrial revolution. It is really a great podcast, and it motivated me to write a podcast about a component of the first industrial revolution. What do the 2020 Mercedes-Benz AMG Project 1, the McLaren Speedtail, the Lucid Air, the Hispanzo Suiza Carmen Bologna, the Delage D12, the Aria FXE, the Aston Martin Valkyrie, the Zenovo TSRS, the Ultima RS, the Zinger 21C, the Koenigsegg Regera, the Koenigsegg Jesko, the Bugatti Chiron Supersport 300+, the Koenigsegg Gemera, the SSC Tuatara, the Hennessy Venom F5, the Pininfarina Battista, and the Lotus Evija have in common with the Industrial Revolution? Horsepower. Each of these vehicles has a minimum of 1,000 horsepower, with the Lotus Evija topping out at 2,000 horsepower. And this beautiful $2.1 million hypercar is an electric vehicle. It's electric. Also, one of the great features about this vehicle is that it powers at 800 kilowatts from 0 to 100% in only 9 minutes. But what does horsepower mean, and where did the term come from? The term horsepower actually comes from the pre-industrial revolution era, and it was used to define the power of a steam pump for the steam engines that were used for mining and assisted in removing water from the flooded mines. Though many consider that the first steam pump came from Thomas Savery, the steam engine's prominent design first began with Dennis Papin. Papin was an inventor who worked with the chemist Robert Boyle in the 1670s. In 1679, while working with Boyle, Papin conceived and developed a steam digester, which was a high-pressure cooker that allowed people to extract fat from animal bones. The steam digester was a container with a tightly closed lid. As the water heated, this tightly closed vessel would confine the steam. This confined steam would then raise the boiling point of water. While working with his steam digester, Papin discovered that the atmospheric pressure of the digester provided mechanical power to the system. His observation of this inspired him to create a high-pressure system within a cylinder. As the water boiled and condensed, atmospheric pressure would cause a piston at the top of the cylinder to move downward, thereby creating a movable system. Papin's piston steam engine was the beginning of the first industrial revolution. On July 2nd, 1698, the British inventor Thomas Savery wrote up a patent that described, quote, a new invention for raising of water and occasioning motion to all sorts of millwork by the impellent force of fire. This was the beginning of the steam engine, also known as the steam pump. A month after he wrote his patent, on June 14, 1699, Savery presented his steam pump to the Royal Society. This original steam pump was a furnace that held a boiler on top. The boiler would distribute the steam to the two cocks at the top, which conveyed the steam by turns to the vessels. As the steam entered the top, it would discharge out through a valve that was also on the top. There was a force pipe that forced hot water out and a sucking pipe that pulled water in from the water source, which was at the bottom of the mine. It was a simple engine. It had no piston and it expended a great deal of high-pressure steam to heat up water. The engine's joints were not strong enough to handle the pressure, which caused a safety problem for deep mining. Finally, the entire apparatus worked hard at expending energy against a condensed steam vacuum. Unfortunately, it could only work at a depth of 30 feet. Nevertheless, Savery took legal measures to make sure that his patent would last for 21 years. This measure was coined the Fire Engine Act. Then, around 1712, Thomas Newcomen designed the next generation of this steam pump. Newcomen designed this engine to pump water from a deeper source using a combination of Papin's pump and Savery's steam engine. Also, Newcomen's invention changed the design of the receiving vessel. Thus, the vacuum that was used to draw in water was replaced by a piston. Newcomen's design included a furnace, a boiler, a capsule for steam, a condensing cylinder, an injection pipe between the condensing cylinder and the top of the cylinder, and a piston at the top of the cylinder. The furnace would heat water in the boiler. This boiler created steam that eventually escaped through a condensed cylinder when the steam inlet valve opened. While the steam sat in the condensing cylinder, a mechanism injected a stream of cold water into the base of this condensing cylinder. As a result, the steam quickly cooled down, thereby creating a vacuum. Since external air pressure is heavier than the air in the vacuum, this would cause the piston to drop down. Once the piston was at the bottom of the condensing cylinder, the process would start all over again, creating steam that would push back up the piston. It was a brilliant idea that had only one big problem. It used Savery's invention, which was patented. As a result, Newcomen was forced to go into partnership with Savery. This was probably a good thing, as the partnership enforced Newcomen's name on the invention. Papin wasn't so lucky. Savery never gave credit to Papin for the use of the piston. Then we come to the third generation of the Industrial Revolution steam engine, as invented by James Watt. James Watt, born in 1736, came from a brilliant family. His mother was Agnes Muirhead, who was affluent and educated. When Watt was 20 years old, he took a job at the University of Glasgow making astronomical instruments. While working at the university, he became fascinated with the steam engine. Watt understood that Newcomen's design was not ideal. It expended a lot of energy in the process of cooling down the steam in the cooling cylinder. In 1765, Watt realized that instead of cooling the steam in that cooling cylinder, he could condense the steam in a separate condensing cylinder. He continued to work with this, and 11 years later, he had a working prototype and a product to market. Watt was not only a brilliant scientist, he was also a clever businessman and a brilliant marketer. He realized that his new engine could replace the work done by horses. He calculated the number of horses that his engine could replace, thus coining the term horsepower. Then in 1801, Richard Trevithick began experimenting with steam engines, creating his first steam-powered passenger vehicle that he called his, quote, puffing devil, or Puffer. The Puffer had a short run and lasted only a few days, when on Christmas Eve, after using it to move passengers around, it caught fire. Trevithick did not give up. 3 years later, at the Penydarren Ironworks in Wales, he built the first steam-powered locomotive that ran a 9-mile-long track. It was a success. This first steam locomotive pulled 5 cars that held 70 ironworkers and 10 tons of iron. However, it could only move about 5 miles an hour, and it only worked 3 times before the rails broke. Nevertheless, this was the beginning of the first industrial revolution, which was the age of mechanical reproduction. So, what exactly is the scientific definition of horsepower? When Watt came up with the name, it represented foot-pounds per second. Watt calculated that in 1 minute, one horse could lift 150 pounds up a 220-foot mine shaft. As a result, 1 horsepower came to be defined as 150 pounds times 220 feet, all divided by 60 seconds. When you do the calculations, it comes out to 550 foot-pounds per second. The mathematical definition of horsepower is defined as power equals work divided by time. And so by the late 19th century, steam-powered trains had an output of about 700 horsepower. It is this power, along with torque, that gives our automobiles the speed that we need. By 1904, the first Model C Ford had a 10-horsepower engine. By the 1930s, the Model A Ford had a 3-cylinder engine with an output of 24 horsepower. 20 years later, we had the muscle cars of the 1950s. The 1957 Chevy had a V8 engine that put out 162 horsepower. When I was in high school in the early 1980s, I drove a 1978 yellow Dodge Dart that had a V8 engine with 195 horsepower. By 1992, the BMW M5 had a 4.9L V8 engine and produced 400 horsepower. Thus, in the cars that we drive, the relationship between engine power and torque is expressed as horsepower equals torque times revolutions per minute, all divided by 5,252, which is a constant. The torque is actually represented as foot-pounds. And here we are, almost 350 years later, in an age where electric cars can go 0 to 60 miles per hour in under 3 seconds. The Lotus Evija electric car produces almost 2,000 horsepower, and it's an all-electric, all-carbon fiber car that can go from 0 to 186 miles per hour in 8.6 seconds. This vehicle is almost perfect. However, like the proletariat factory wages of the Industrial Revolution, the only thing standing in the way between that vehicle and us is the $2.1 million that we would need to buy it, or a well-connected friend who can set us up with a test drive. I'm Gabrielle Burchak with Math, Science, History, and until next time, carpe diem. For images of the Piston, Savory's Pump, and New Coman's Pump, please come visit me at mathsciencehistory.com for further explanations. And while you are there, if you like what you're listening to, please feel free to click on that coffee button and buy me a cup of coffee. Until next time, carpe diem.